Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Look closely at a sunflower head, a pine cone, or the core of a cabbage. What you are seeing is not just biology, it is a masterpiece of applied mathematics. Nature's most common geometric signature is the spiral, and almost universally, these spirals are defined by one number: the golden ratio, or its angular counterpart, the golden angle. Approximately 137.5 degrees. This isn't a coincidence. It is one of the greatest triumphs of natural optimization, known as phyllotaxis. It dictates the perfect arrangement of leaves, seeds, or florets around a central stem. The 137.5 degree angle ensures that each new element grows precisely at the point that maximizes the distance from all previous elements, preventing overlap and ensuring optimal access to sunlight and resources. This arrangement is so efficient that the count of spirals, in either clockwise or counterclockwise directions, almost always yields two consecutive numbers from the Fibonacci sequence, like 8 and 13, or 21 and 34. This system works flawlessly because it operates within the constraints of Euclidean geometry. That is, it assumes the surface the seeds are growing on is flat, or planar, like a disc. But what if the angle fails? What if, due to a genetic mutation or unusual growth factor, the angle of divergence deviates, even slightly, from that perfect 137.5 degrees? This is where we encounter the golden angles glitch, and where plant life appears to abandon the stable, predictable world of Fibonacci for something far stranger: hyperbolic geometry. Imagine a world where the laws of space itself are different. In our familiar Euclidean world, flat space, if you draw a triangle, the internal angles always sum to 180 degrees. But in hyperbolic geometry, a non-Euclidean space characterized by negative curvature, think of a saddle shape or the frilly edges of certain corals, the internal angles of a triangle always sum to less than 180 degrees. For plants, the result of a deviation from the golden angle is catastrophic for packing efficiency. If the divergence angle is even slightly off, say 130 or 145 degrees, the system breaks down. Instead of forming tight, optimal spirals, the elements suddenly become loose and inefficient. Mathematically, the plant tissue is trying to tile a surface that, if you flattened it, would require continuous stretching and wrinkling. This is precisely the behavior found in certain genetic mutants, particularly those studied in maize and, famously, in abnormal sunflower development. When the genetic mechanisms controlling the spacing of primordia, the tiny buds that become seeds or leaves, are disrupted, the resulting structure is not just messy, it mathematically mirrors a projection of a hyperbolic tiling. Consider a regular Fibonacci sunflower. The seeds are packed so tightly you can barely see the spaces between them. Now, look at a theoretical hyperbolic variant. The growth attempts to fill the space by forming many more, much looser spirals, often resulting in complex, overlapping, and highly irregular patterns. The structure physically attempts to occupy a higher dimensional space than the flat plane it is confined to, resulting in a frillier, or puffier, appearance. Scientists use this deviation to better understand morphogenesis, the biological process that causes an organism to develop its shape. By simulating these glitches in computer models, researchers can map out the precise mechanical and chemical thresholds that keep a plant locked into the perfect Fibonacci optimization. They found that the golden angle acts as a powerful attractor. The system naturally wants to revert to 137.5 degrees because it is the most stable and energy-efficient solution. However, when certain genes responsible for the signaling pathways, like those that regulate the plant hormone auxin, are mutated, the primordia are positioned too close or too far apart, forcing the mathematical system into an unstable, non-Euclidean state. Perhaps the most extreme visual evidence comes from certain cauliflower varieties, though the classic Romanesco involves fractal branching rather than pure hyperbolic tiling. In the lab, manipulating the growth environment can force plants into patterns that definitively cannot exist in flat space, forcing them to overstuff the surface, creating structures that look like they belong in a non-Euclidean universe. These patterns offer crucial insights into the sheer complexity of biological geometry and remind us that mathematics isn't just an abstract human invention. It is the fundamental operating code of nature. Even when plants seem to break the rules, they are simply adhering to a different, more complex, and far weirder set of geometric laws. For more incredible facts like this, don't forget to subscribe and turn on notifications.